Okay. Thanks everyone for coming. It's nice to see so many of you here. So today's talk is jointly organized by the Digital Archaeology Group and also the Material Culture Talks, LASSE. And today we have Guilherme D'Andrea Curra talking about his research. And he did his master's here in Leiden a couple of years ago. Yeah. Then moved back to Brazil, was working on his PhD, and both his master's and the PhD are about using machine learning on pottery and typologies and stuff like that. And I think the introduction short, so go ahead.
Okay, thank you, Alex. So, good evening. Those guys told me that it will be just a small public, but I'm not. I didn't expect so many of you. Thank you very much for being here for this presentation. Special thanks to Professor Lambers, which is my supervisor, and Dr. Brackman, my co-supervisor, who suggested this presentation. And thanks for Alex and Les for organizing it and supporting, and also for Faculty of Archaeology in general for also supporting this presentation. And okay, this has Alex mentioned, it started, this research started after I concluded my master's in 22, 2.5 years ago. And when I come back to Leiden for my graduation ceremony and for the presentation of the results of the research in Cologne, Germany, at the CAA conference, Computers Application in Archaeology conference, then an idea appeared that this research could be continued in some way in the PhD level. Then after talking with Professor Lambers and after a certain period to prepare a research proposal and it was accepted, I started 1 year ago, and also I was lucky enough to have Dr. Brackman as a co-supervisor and accepted this challenge. And so this is the results of the first. This is the result of the first year of research. So this presentation is planned to last between 20 and 25 minutes. But since it is the first time I do it, something goes in an unplanned way. I hope not. And of course, I will welcome your feedback in the end. Thank you. So, let's begin. Analysis of clustering algorithms and performance evaluation metrics applied to samples of Tell El-Yahudiya ware typology. This is how the presentation is planned. This presentation is related to a PhD research on pattern recognition methods, especially unsupervised learning, combined with analytical tools and interpretive approaches for constructing pottery typologies in archaeology. In the first stage of this research, different clustering algorithms are applied to a pottery dataset with an already defined chronocultural typology to evaluate the potential that algorithms built with different concepts and several combinations of parameters have to replicate the original expert typology. Several combinations of features are considered. Clustering performance is being evaluated through both ground truth-based metrics and model-only based metrics. This research aims to contribute to understanding of how pottery typologies can be constructed, starting with already established typologies, and then applying this knowledge to unclassified assemblages or assemblages classified long ago and that have potential to be reanalyzed under new approaches and perspectives. More specifically, it considers the identification of the most relevant vessel morphological differences in unsupervised learning methods and additional questions such as the description of the more complex cultural components of vessels, such as decoration, in order to be processed by clustering algorithms. So about typology, is one of the fundamental aspects of archaeology as a discipline and a basis for answering more complex research questions related to human activities in the past, such as integration among cultural groups and the exchange of goods and ideas. The aim of clustering analysis is to construct groups with homogeneous properties out of heterogeneous samples, or defined in terms of their internal cohesion and external isolation. The two fundamental steps to achieve this objective of clustering analysis are: first, the choice of a proximity, similarity, or distance dissimilarity measure, depending on the point of view, among each pair of observation samples. The second point is a choice of a group building algorithm based on the first step so that differences between groups become large and samples in a group become as close as possible. So this is how the typical Yahudiya ware looks like. It's red or brown to black polished jug with white incised decoration, usually small in size, less than 12 centimeters high in average, with few larger exceptions. They appear in a number of different shapes and decoration styles. This ware has been studied since the late 19th, early 20th centuries, with the contribution of several scholars, which proposed some origins hypotheses and a number of typologies, which culminated with the more recent and inflation studies from Kaplan and Bietak in the 80s. This is the latest typology proposed by Aston and Bietak in 2011. They still use the geometric types defined by Kaplan as a general reference, but they propose now a definition of types based on a chronocultural approach, with the evolution of types according to different periods and geographic locations. The periods appear in the top. So the types highlighted in yellow are the ones included in the research assemblage. This is an example of how the typology was constructed. This is relevant for the research because these different levels of detail have branches, types, and subtypes. Subtype is a terminology that I use. Originally, they are all types for the authors, but I choose this term subtype to differentiate this from this level. And they are based on vessels' origins, shape, decoration, and vessel details such as rim, base, and handle types. So there are hundreds of different types in this typology proposed by Aston and Bietak. If you consider this lower level are individual types. The distribution, this ware has been found from northern Levant all the way through Egypt and Sudan in the south, depending on particular types and periods. Some types were found in the north, starting with Cyprus, and the earlier types and the later types were found here near to Sudan. This is the chronology of the archaeological site of Tel Daba, where this assemblage comes from. And the site was occupied since the early Middle Kingdom in Egypt under the Roman period, until the Roman period. And this Yahudiya ware was being most characteristic of the second intermediate period. In Egyptian history between 18th and 16th centuries BC, or the Middle Bronze Age too, in the broader Near Eastern chronology. The research dataset was based on a publication by Aston and Gietak and consists of 272 samples representing 7 branches and 23 types in the Yahudiya typology. Uh, 16 different features were used to characterize the samples, including vessel measurements, year decoration, ring and base types, and also ceramic technology features. The features were obtained directly from the catalog of vessels. The types, descriptions, it was a section separated from the catalog. In case of ring and base types and handle types, while the detailed decoration description was a particular challenge in this research, because I had to find a way to convert this textual description in something more structured. Then I used code based on keywords. So this type of description was converted in keywords and finally in a alphanumeric code. The categorical features are converted into binary features by encoding methods, because machine learning algorithms work with numeric features. So there must be a kind of conversion from categorical to numeric or binary coding. So now talk about the methods applied to the data. The general idea is that a series of clustering algorithms are executed under several combinations of parameters and different versions of the data set based on feature selection, dimensionality reduction methods like PCA, physical component analysis, and the resulting clusters are initially evaluated by different performance evaluation metrics. 6 clustering algorithms were applied. Those are based on different group building methods and allow the utilization of diverse kind of parameters. Some of these algorithms allow the selection of the distance metric used, if it is Euclidean, Manhattan, or cosine, while others, this one here, works with a graph distance metric. They also can be characterized by how the number of clusters is defined, if directly, like here in this case, or indirectly through a number of different parameters. Up to 4 parameters per algorithm can be defined by the analyst, plus parameters that are fixed. When the algorithm allows, the number of resulting clusters can be informed by the analyst, or it's defined as an output parameter otherwise. So 9 different performance metrics are being recorded, both ground truth based, when the class or the type of the sample is used as a reference, and model based, when there is no previous reference to be compared. At the present moment, the first 3 are being used to analyze the results: homogeneity, completeness, and V measure, which is the harmonic mean between the two. Three different versions of the Yahudiya typology are being used as ground truth, each one analyzed separately. The 7 type level is based on the main branches. The 13 type is based on a traditional typology, formerly defined by Kaplan and Biatak, which is still used as a general reference. And this is the most complete version, where 23 types are based on the second level of detail of the typology. So combining the different algorithms, the 3 versions of ground truth types, and then the diverse data set configurations based on feature selection, or for instance, instead of using all 16 features, I just use a subset of those features, right? Focusing on shape and decoration, and also only in ceramic technology. So it's possible to record 90 different combinations of results, including the 2 variations of PCA. So this is an example of how the results of the tests are recorded, including the ground truth type version, parameter combinations, and performance metrics. This was made manually, but I hope in future versions to generate this automatically. Okay. For selected results, contingency matrix of types here and clusters is generated, where we can analyze how samples of each type were associated to different clusters. So based on the contingency matrix, 2 main types of analysis can be performed. Completeness analysis focuses on how individual samples of one specific type, for instance, the L2 type. These are all samples of this type in the research assemblage. How these samples were associated or split into different clusters according to different algorithm variations. The other kind of analysis is the homogeneity analysis, which focuses on how different types were associated to specific clusters, again, based on different algorithm variations. So we have the type perspective and the cluster perspective. This is the software used to access the data set and execute the algorithms. And now I start to present some results of the research so far. A total of 902 tests were performed. From these, 17 were selected for detailed analysis according to the performance metrics and their correspondence matrix. And the number of types, clusters, and samples were analyzed individually. This is the overall results of how the different algorithms performed under the different versions of the data set. These are the results with the highest performance, the number columns in the right. in each case, for some algorithms and type versions, different versions of the data set, for instance, the version based on shape and decoration worked better than for others. Okay, so generally the all features version worked fine, but also some versions also produced interesting results for some variations. Okay, so all 5 versions of the data set were useful for analysis in some way. Here we can see how two cases of all samples can be distributed through the contingency matrices. These two algorithms variation, these two types of algorithms, have a similar V measure, here V and there, but different values for completeness, C, and homogeneity. So result in very different configurations, distribution of the samples across the types and clusters. So looking just at the numbers, we cannot have complete idea. It's necessary to look at the visually for the moment to see that, for instance, this one here looks more well balanced than the other one. All right. Just we'll make a quick stop to drink water. This is a summary of how samples of different types were associated among each other, considering 12 algorithm variations. The numbers represent the quantity of clusters in each association. The cells in dark green represent the highest quantities. This table is a summary of the previous image. For instance, all samples of these 3 types here, L2, L4, and 5, they're more frequently associated together than samples of other types. So there is a kind of relation between the sample of these types, stronger than in the other cases. This table shows which are the types that resulted in higher completeness, meaning that their samples were usually not associated with samples of other types. Now I'm going to look at one specific example, cases through the analysis of how samples of the L2 type here were distributed across different clusters. We can see here that samples belong to 6 different subtypes here in this column. And these characteristics of the samples is strongly associated with their different association. Taking an even closer look at the research data set, we see that this vessel here is the only representative of its subtype. It's the only of this L21 subtype. And it has significant differences compared to samples of other subtypes, especially its size. You can see the rate and belly diameter. It's easier to see with the vessel pictures in scale. The vessel on the left was always associated in a separate cluster, while samples of other 5 subtypes were associated according to different criteria, depending on the algorithm's variations. For instance, in some cases, these 2 subtypes are associated together, in other case, completely separated. But this one here always separated from the others. For instance, this is a summary for some the types that were analyzed in detail. Here for the L2 discontinued example. Despite a low completeness here, where it means that their samples were separated among different clusters. They have enough similarities, the samples, to be included in one main cluster. For instance, in one case, all 13 samples were included in one cluster, apart from the big one. So they have enough similarities to be associated with just one cluster. But in other cases, they have enough dissimilarities to be split into 4 clusters according to their subtypes. So depending on the algorithm configuration, we can see a more close aggregation between samples, or as they can be more split. So it's up to us to define which is our interpretation on this. So, just returning. In the case of here, for instance, this type here is the only type that is handmade. So it differs from all the other types of this Yahudiya ware. In most algorithms variations, samples of this branch were not associated with samples of any other type. There are some exceptions, but generally they are always associated in separate clusters. Now the other kind of analysis, the homogeneity analysis. So independent of the performance metric of the corresponding algorithm, the detailed observation of their clusters may indicate different criteria for association of samples, especially those that belong to different types. So you can see how the algorithms are behave very differently from comparing the results. Some have a higher homogeneity, others lower. But it's interesting to see how samples from different. I'm interested in understanding why samples of different types were associated together. For instance, this part here is okay, in principle, because the samples belong to the L branch, so they have some kind of similarity. But why this one here was included in the L type, for instance? For instance, this cluster includes 2 samples from 2 subtypes of the I6 type. The majority of samples belong to the other type, the subtypes of the L branch. Those types that we saw before that were usually more aggregated together. But why this one here was included in this cluster? So despite these types being culturally and chronologically associated with the general preform type, they have a slightly biconical shape. This one here especially. So it was like 2 of the L2 and L4 subtypes, which also have a biconical shape. So they belong to biconical type. So this kind of shape was the main factor used by the algorithms to aggregate these different types. In this case, okay. Okay, now the discussion part. Performance metrics are generally useful for the initial selection of algorithms results and overall evaluation of clusters. Other steps are necessary to evaluate the coherence of the clustering results, which are the resulting number of clusters when not informed by the analyst must be considered, because if I'm working with 13 clusters as expected, and I receive 40 or 50 clusters in results, so it's not interesting for this specific case. And sometimes the performance metrics go up, but the result doesn't make sense in number of clusters. Detailed analysis of contingency matrices when based on ground truth metrics, completeness and homogeneity analysis of types and clusters, and observation of individual samples and the content of their features. When algorithms variations produce different results for one specific type, for instance, samples are divided into 2, 3, or 4 clusters, more than one solution can be considered satisfactory, since the same vessel can be grouped in more than one way, depending on the criteria used in the process and how the typology was defined. It is possible, in most cases, to interpret the overall clustering results, especially how samples of different types are associated through the general typological description by Aston and Biatak, the authors. So, clustering algorithms are a viable alternative as a priori method to group vessels, samples with typology definition in mind, and additional methods must be used to analyze, refine, and complement them. So, hence this is an ongoing research. I already have some next steps planned. More shortly, horizon, the analysis of results of additional versions of the typology. I showed you the 23 type version. They still left the 7 type and 13 type to analyze. Analysis of other performance metrics, especially the model-based metrics. Allow the selection of a subset of the data set, for instance, analyzing specific types only, especially those that have a minimum number of samples, and proceed with the quantitative analysis of the contribution of individual features to the selection of samples for cluster formation, because the analysis so far in this respect was made in a qualitative way, looking at the data set and analyzing each case. The second part of this research is related to a solution to increase the automatization and productivity of the performance analysis of clustering algorithms, allowing the evaluation of additional data sets, integration of the process components, which are algorithms, parameters, dataset variations, clusters, and samples visualization, in an iterative and exploratory way. The inclusion of different additional elements in the parameters, such as different weights for specific features, because this can influence the results. And evaluate the possibility of applying the concept of cluster ensemble to take advantage of stronger aspects of different algorithms, because each algorithm has some strong and weaker points, and in some cases, the results of just one algorithm is not enough to have a complete idea of the possibilities of the typology. Okay, the sources and the end. Thank you very much for your attention.